Welcome back to the deep dive. Our mission here is always the same. Take a mountain of complex technical sources, stack them up, and distill the engineering insights so you, the listener, walk away with the critical knowledge needed to stay ahead. Today we were soaring into the future of transportation, specifically urban air mobility or UAM. And we're looking at one project that, well, it stands to fundamentally rewrite the rules, P13. We hear a lot about eVTOLs, these electric vertical takeoff and landing aircraft, and usually the conversation hits a wall almost immediately. And that wall is range. How do you move past the limited reach of pure battery power?
Right.
The answer for the P13 is radical, hybrid power, coupled with a modular architecture. But, introducing hybrid systems into an aircraft environment, it doesn't just double the complexity.
No, it multiplies it exponentially. It creates a foundational tension. And our deep dive today is into the engineering specification for the absolute control center, the digital brain of this P13 modular system.
Okay.
We're talking about the vehicle control unit, the VCU, which handles all the ground and power dynamics,
Right?
and the flight control computer, or FCC, which is what keeps the aircraft safely in the sky.
And when you put them together.
When combined, this hybrid control unit, or HCCU, is responsible for a seamless experience that quite literally has to merge a high-performance long-range car with an 8-rotor aircraft.
And here's the kernel of the entire episode. Our sources confirm that this VCU FCC cannot merely operate in two domains. It has to be certified to the highest standards of both.
That's the core challenge.
This P13 system has to resolve the technical and, frankly, the cultural complexity of bridging automotive engineering, governed by the functional safety standard ISO 26262, and aerospace engineering, which is defined by the incredibly rigorous software and hardware standards DO 178C and DO 254.
And every single line item we're going to analyze today is a direct response to that unprecedented dual mandate.
Okay, let's unpack this. We'll use the McKinsey-style top-down approach that was mandated in the preliminary project documentation. So we start with the strategic why. Why did P13 even choose this incredibly difficult path?
Well, it all stems from the fundamental constraints that are crippling these first-generation eVTOLs.
The UAM dilemma.
Exactly. And it's laid out clearly in 3 parts. First, and this is the big one, the unavoidable battery density bottleneck.
Right. The chemistry problem.
It's pure physics. We are still stuck with energy density at the system level hovering between, say, 200 and 250 watt-hours per kilogram.
Which isn't much when you're trying to lift something vertically.
Not at all. That physical limitation imposes a non-negotiable range cap, often pegged around 150 kilometers for practical payload-carrying urban missions. Now, that range is fine for intra-city hops.
Flying from one side of town to the other.
Yes, but it immediately fails to meet the long-haul, regional transport demands that UAM promises to solve. If you're trying to fly from, say, Boston to New York or London to Paris, 150 kilometers is a complete non-starter.
And the economic reality of that bottleneck is challenge number 2, infrastructure scarcity. Even if the batteries could somehow handle the range, the time it takes to recharge them is just prohibitive for a high-utilization operational model.
You can't build enough charging vertiports fast enough to handle high-volume traffic.
You're just swapping revenue-generating flight time for non-revenue-generating downtime, waiting for a high-powered DC fast charger to become available.
And this is where the P13 team showed some real foresight. They recognized the third crucial challenge, the last mile problem.
Okay.
Even if you fly efficiently, once you land at the vertiport, how does the passenger complete the final leg of their journey? A dedicated aircraft can't solve surface transport connectivity.
Right, you still need a car, a taxi, a train link.
So P13 integrated the solution to the last mile directly into the primary architecture.
And here's where the strategy shifts from just, an incremental improvement to something revolutionary. The P13 modular solution is what they call land-air separation.
It's a genius stroke of engineering simplification, but it's achieved through functional complexity. It's quite a paradox.
So what does that mean in practice?
The P13 doesn't just use hybrid power, it formalizes the separation of functions. The mothership is positioned as the dedicated mobile energy platform. It's the long-range, high-endurance, ISO 26262 certified system.
It's essentially a rolling power station.
Exactly. Then the flight module is stripped down to be just the dedicated aerial lift mechanism. It's optimized purely for lift, thrust, and rapid vertical maneuverability, and it's certified to aviation standards.
Let's nail down those specs, because the contrast here is just staggering. The mothership is a beast, a 6x6 all-wheel drive vehicle using a plug-in hybrid extender power source. And the key metric here is range.
Greater than 1,000
So
kilometers.
1,000 kilometers, that's intercontinental capability. It's rated for 4 to 5 persons, and crucially, its safety certification is focused on the automotive world, ACLD.
Then you look at the flight module, which is designed for entirely different parameters. It uses an 8-motor distributed electric propulsion, or DEP, system.
Yeah.
It runs on high-energy density lithium batteries. But they're designed for quick bursts, not endurance.
Because it doesn't need to be.
It doesn't. It only has to power the short flight segments, and then it can rely on the mothership for replenishment. And this architecture allows it to support up to 6 flights per charge cycle, carrying 2 people. The design imperative is maximizing that lift-to-weight ratio.
And its safety certification, of course, has to satisfy the FAA and EASA's aerospace standards.
Of course.
So we have 2 machines optimized for completely different objectives, one for massive range, the other for high reliability vertical lift, and they have to connect in the middle of a mission. This brings us right back to the hero of our story, the VCU-FCC as the unifying controller.
It's the diplomat and the traffic cop all rolled into one. The VCU-FCC, or the HCU as we call it, is where the rubber literally meets the sky.
And the challenge.
The unprecedented challenge lies in coordinating subsystems that speak completely different temporal languages. The ground side, managing the 6x6 transmission, the ICE, the charging processes, it operates on response times in the tens of milliseconds. That's typical for automotive dynamics. A little delay is usually acceptable.
But the flight dynamics.
Flight dynamics demand hard, real-time precision. We're talking about millisecond or even sub-millisecond control loops for attitude stability and for commanding those 8 DEP motors. If your flight controller has a 10-millisecond delay when it's correcting for a sudden wind shear, the aircraft becomes unstable.
So the VCU-FCC has to be bilingual. It has to transition seamlessly between these 2 operational speeds.
Precisely. So if we define it, the VCU-FCC is the mission-critical cross-domain control system. It has to ensure seamless energy management, high-precision mechanical coupling, and above all else, uncompromised certified flight safety. It is the single point of contact that determines success or, well, catastrophic failure for the entire P-13 concept.
And we have to emphasize the physical precision required. You look at the flight module parameters. 480 kilogram max payload, 620 kilogram operational weight. But the truly shocking specification is the docking requirement.
Yes. The HCU must ensure the 2 vehicles physically link with a maximum mechanical tolerance of just 5 millimeters.
Wait, plus or minus 5 millimeters, that's smaller than a pencil eraser.
It is.
When you have 2 massive vehicles, one on the ground with active suspension, the other gently maneuvering above, coming together, potentially in wind or on uneven ground, how is that tiny margin of error even maintained? That seems less like engineering and more like orbital mechanics.
It absolutely is. That 5-millimeter tolerance requires a fusion of sensor technologies that goes way beyond standard automotive perception. We are talking about high-speed LiDAR, coupled with synchronized stereo cameras processing data at hundreds of frames per second.
Just to figure out where everything is in space.
To calculate the relative position and orientation, the 6 degrees of freedom, or 6 DOF of the flight module relative to the mothership's docking port. And crucially, this precision has to be maintained not just statically, but during the posture adjustment phase.
Where the mothership is actually moving.
Yes, it's actively using its 6-wheel suspension to squat or shift its stance, compensating for any ground slope. The controller is managing massive forces to achieve this tiny precision. It is the highest expression of that cross-domain requirement.
Achieving that kind of precision and safety requires a rigid, logical structure. And this is where the MECE principle, mutually exclusive and collectively exhaustive, comes into play. Detailing the architecture needed to ensure fault isolation and prevent common mode failure. You have to architecturally guarantee that a failure in, say, the ground system's network driver can never, ever compromise the flight control software.
That principle of freedom from interference is foundational. The structure is based on 3 layers, and we have to start at the top, L1, which has the ultimate authority.
2.1 L1 strategy layer, the FCC flight control computer. This is the air traffic control for the whole operation, the flight commander.
Its core role is strategic, executing high-level flight tasks, calculating the trajectory, and, crucially, attitude stabilization. But the single most important safety feature that lives in L1 is envelope protection.
The software guardrail.
It's the software guardrail that prevents the pilot from commanding the aircraft to perform maneuvers that would exceed its structural limits or stall it or overstress the rotors, especially in degraded or failure modes. It acts as the final decision authority on all safety margins.
And structurally, this L1 authority is protected by the highest level of redundancy. Our sources mandate a triplex, triple redundancy, heterogeneous hardware architecture.
Right.
Now, this isn't just copying the same ship 3 times. Tell us why heterogeneous is the key word here.
It's the direct defense against common mode failure.
Right.
If you use 3 identical processors running the exact same software, a single unforeseen bug in that software or a known weakness in that specific silicon will take down all 3 channels simultaneously.
Which is catastrophic.
It's CCF, and it's catastrophic. By using a heterogeneous approach, maybe different processor families or different compilers, or even slightly different implementations of the control law, you minimize the probability that a single fault will affect all 3 channels.
And then they vote.
The voting algorithm compares the outputs in real time. If one channel disagrees, it's isolated and effectively outvoted by the other 2, allowing the mission to continue safely.
That complexity comes at a massive cost, both in hardware and validation, but safety demands it. So the FCC receives inputs, pilot stick commands, data streams from the IMU for acceleration and rotation, and the air data computer for airspeed and altitude. What does it output?
It outputs the high-level request, the total thrust vector command. It basically tells the system, I need X amount of upward force, Y amount of roll moment, and Z amount of yaw. But it doesn't care how that force is generated.
That how is the job of the middle layer. Which brings us to L2, the crucial bridge between the air requirements and the power source capabilities. 2.2 L2 tactical air. The VCU-HPCU, hybrid power control unit. We called this the energy brain.
L2 is the tactical general. It manages the energy flow. Its core functions are executing the energy management strategy, or EMS, deciding when to run the ICE, when to charge the batteries, when to prioritize quiet electric flight. It also handles all the mode switching logic.
But its most demanding role is what you call thrust arbitration.
Yes, and that's where the hybrid tension really lives, isn't it?
Seems like it.
The VCU receives that clean, stable, total thrust demand from the FCC at L1, but then it has to decide in real time how to achieve that demand using the available resources. It monitors the battery state of charge, the motor temperature, are we overheating the P3 drive, and the engine status, is the ICE spun up and available.
So it's a constant balancing act.
An instantaneous, complex calculation. If the SOC is low and the temperature is nominal, the VCU might assign 70% of the demand to the ICE P1 system and 30% to the battery-fed P3 motor. And on top of all that, it's also responsible for controlling the most critical mechanical component, the K0 clutch engagement timing.
The required redundancy here is different from L1. We move from triplex to a dual duplex, active hot standby architecture. Why the slight reduction in redundancy for L2?
Well, it reflects the function. While L2 is mission critical, it's managing tactical power, not primary attitude stability. L1 provides the safety envelope. L2 provides the power optimization.
Okay, that makes sense.
Dual duplex provides that guaranteed millisecond level seamless failover without the extreme complexity of a triple voting system. If the active unit fails, the hot standby unit has to take over in under 20 milliseconds.
And that ensures the thrust fluctuation is minimal.
Minimal. Less than the 2% defined in the KPIs, which prevents the aircraft from pitching or rolling when that transfer occurs.
And finally, we delegate the specifics down to 2.3 L3 execution layer. This is where the actual muscle works.
L3 consists of the dedicated controllers for the physical components, the engine electronic controller, the EEC for the internal combustion engine, the motor controllers or inverters, the MCUs for the 8 DEP motors, and the battery management system, the BMS.
So L2 tells L3 what to do.
L2 tells L3, I need 500 nanometers of torque from MCU number 4. L3 then executes the low-level closed-loop control, the PID loops, to make that happen. Fault isolation is still vital here, but these components operate on simpler, dedicated control logic.
None of this highly deterministic architecture functions without an equally deterministic communication network. Let's talk about 2.4, the hybrid communication backbone. Our sources split the network based on criticality.
Yes. For the L1 to L2 link, the most critical control path, we need deterministic, time-triggered communication. We can't rely on traditional Ethernet, which is susceptible to congestion and timing uncertainty.
So the backbone requires aviation-grade systems.
Things like T-to-Tethernet, that's SAE AS6802, or AFDX, which is ARNC 664 Part 7.
What's the fundamental difference between standard Ethernet and TT data? Why the cost and complexity?
Standard Ethernet is best effort. It's great for your office network, but there's no guarantee on when a message will arrive. Ethernet implements a time-triggered protocol. It's essentially synchronized by a global time clock across the entire network, and every critical message transmission is scheduled into guaranteed time slots.
So it's predictable.
Completely predictable. This means we can guarantee that the control loop periods are less than 1 millisecond, and crucially, the timing jitter, that tiny random variance in delivery time, is less than 50 microseconds. That's acceptance criterion AC is where 1.
And if you didn't enforce that?
If we didn't enforce that, the entire triplex voting mechanism in the FCC would fail because the 3 processors wouldn't receive their inputs at the required synchronized microsecond. It would all fall apart.
So deterministic network for control, and then for the rest of the peripheral communications.
For the peripheral network, L2 to L3, we use dual redundant CN-FD. This runs at a high rate, 5 MIT-bits, which is sufficient for command and status updates to the MCUs, BMS, and the EEC.
And it's robust.
It's highly reliable and robust, specifically designed to function well in harsh electromagnetic interference, or EMI, environments. And given that the VCU FCC is sitting right next to 800-volt high-current cables being switched by high-frequency CZ inverters, that EMI resilience is absolutely non-negotiable.
So it's a necessary trade-off.
Exactly. Use the simpler, robust, high-speed protocol where determinism isn't life-critical, and reserve the complex Ethernet for that core control loop.
We've established the architecture. Now we get into the specialized software that makes the P13 function, and this is where the engineers truly earn their stripes. These are the algorithms that solve the unique hybrid challenges. Let's start with 3.1 VCU's hybrid coordination functions.
We can begin with FUNC VCU-01, torque fill. This is a perfect example of the VCU managing the inherent limitations of mechanical components with instantaneous digital power.
And the challenge, as noted, is the internal combustion engine's slowness, turbo lag, throttle body response delay, all that inertia.
Precisely. If the FCC suddenly demands a 50% increase in thrust, the ICE might take 200 milliseconds to ramp up. That delay is unacceptable. It destabilizes the attitude, especially in a hover, and it could easily violate the flight envelope.
So what does the VCU do?
The VCU recognizes this instantaneous power gap and activates the P3 electric motor, the primary electric propulsion motor, to instantly output compensatory torque.
So the VCU commands the P3 to generate exactly the amount of power the ICE should be generating right now, but isn't.
Correct. And that command must be executed within 10 milliseconds. The P3 motor acts as an electronic force multiplier, covering the ICE's lag. The net result is that the total thrust delivered to the rotors is linear, predictable, and instantaneous from the pilot's perspective.
It makes the hybrid system feel like a pure electric system.
Which is critical for pilot trust and for certified handling qualities. It's the highest form of electronic masking of mechanical limitations.
The next function is perhaps the most delicate mechanical maneuver in the entire system. FUNC VCU-02. K0 synchronization. This is the transition from pure electric operation to engaging that hybrid parallel cruise mode.
This is the high-wire act. The K0 clutch is what physically links the ICE and P1 generator side to the P3 motor and propulsion shaft. If the rotational speeds are mismatched when that clutch closes.
Like, say, one side is spinning at 3,000 RPM and the other at 500 RPM.
Right. The resulting mechanical shock would be catastrophic. You'd likely shear teeth right off the gearbox.
You want a bumpless switch. How does the VCU achieve that synchronization in real time?
It employs the P1 generator, which is mounted on the ICE side, as a motor. The VCU commands P1 to actively drag the ICE, expending a little battery power briefly, until its rotational speed is fully synchronized with the speed of the P3 shaft.
And the tolerance must be incredibly tight.
It is. The speed difference, the delta RPM, must be less than 10 RPM or maybe up to 50 RPM under dynamic loads. Only once this precise synchronization is confirmed, the VCU commands the K0 clutch to gently close.
So the VCU is using electric power to perfectly align mechanical components. That minimizes wear and maximizes passenger comfort. The goal of a bumpless switch resulting in vibration less than 0.05 IPS. That sounds like a comfort metric, but I imagine it's a durability metric too.
Oh, absolutely. While passenger comfort is a market requirement for UAM, that low IPS measurement is a direct measure of the mechanical shock transmitted through the drivetrain. Exceeding that threshold repeatedly means premature failure of bearings, seals, and gear teeth.
So the VCU is acting like a digital mechanic.
Exactly. It's protecting the long-term reliability of that massive investment in the hybrid powertrain by making these minute high-speed corrections.
And even when the engine is running smoothly in hybrid mode, There's an algorithm to keep it that way. FUNC VCU03. Active vibration damping.
ICEs inherently produce torsional vibration, these twisting forces, at specific operational frequencies or critical RPMs. This vibration fatigues materials. So again, the VCU leverages the immediate response of that P1 motor. It monitors the vibration sensors and commands P1 to generate counterphase pulse torque at precisely the same frequency as the unwanted torsional vibration.
Like noise-canceling headphones, but for engine shake.
That is a perfect analogy. It cancels the damaging vibration actively. This not only dramatically extends the life of the gearbox, the coupling, and the transmission components, a huge maintenance and safety win, but it also fundamentally improves the ride quality.
Making a piston-powered vehicle feel much closer to the silky smoothness of a pure electric drive.
That's the goal. These three functions together, torque fill, K0 sync, and active damping, they are the definition of hybrid mastery.
Moving from coordination to control, let's switch focus to the commander. The FCC's unique capabilities, covered in 3.2 FCC's flight and safety functions.
Right. The primary function is FUNC FCC01, Thrust Vector Control, or TVC. With an 8-motor distributed electric propulsion system, pilot input has to be simplified.
Our pilot can't manage 8 throttles at once.
No. The pilot commands a single roll angle, but the FCC has to translate that into 8 complex differential speed and torque adjustments across all motors. To roll left, the 4 motors on the right side speed up slightly, the 4 on the left slow down, and this has to be constantly adjusted for pitch and yaw stability.
So the software complexity allows for a greatly reduced pilot workload.
And enables a single pilot operation, which is key to the business model.
But the real measure of the FCC's integrity comes during a failure. Let's discuss FUNC FCC02, catastrophic reconfiguration. This is the algorithm designed for the worst day imaginable.
It addresses a non-recoverable system failure. Perhaps a total loss of the ICP-1 generator system due to an engine fire or a major battery failure. The FCC must immediately recognize this loss of its primary energy source.
And its response?
Its immediate response is to declare limited energy mode and dramatically restrict the flight envelope. Why? To conserve the remaining critical battery power needed for the final descent and landing.
What specifically gets restricted in limited energy mode? Is it just speed?
It's much more than speed. The system immediately limits the maximum angle of attack to avoid high drag and current draw, the maximum climb rate, to prevent exhausting the remaining energy and lateral maneuverability. It shifts the entire flight control priority from performance optimization to pure survival.
And it helps the pilot find a place to land.
Concurrently, the FCC uses its navigational database and the remaining battery state of charge to perform an emergency landing calculation. It displays the nearest feasible safe landing site and guides the pilot there. It transitions from a complex high-performance autopilot to a highly efficient, simplified emergency guidance system instantly.
That's the core mission profile logic. Now let's wrap Section 3 with the transition back to the ground. 3.3 high-precision automated docking. This 5-minute process, coordinated by the HCU, is the physical realization of the modular concept.
It's a fully automated, coordinated sequence of events that requires incredible real-time data fusion. Stage 1 is perception and alignment. As we discussed, this involves fusing data from LiDAR, high-resolution cameras, and even ground-based ultrasonic sensors. The HCU has to process this data at over 100 Hz to generate a continuous, dynamic, millimeter-level 3D model of the docking scene.
Then comes the mechanical response, posture adjustment.
The HCU commands the mothership's 6-wheel active suspension. If the mothership is parked on a slope or uneven terrain, the suspension actively moves the vehicle's chassis, maybe squatting or leveling it, to dynamically match the flight module's position.
And this compensation is happening at over 100 Hz.
To ensure that critical 5mm docking tolerance is maintained even if the wind is jostling the flight module, the HCU is commanding mechanical forces to counteract dynamic environmental conditions.
Once aligned, we move to the physical connect, mechanical interlock.
This is a complex orchestration of 14 separate actuators. The HCU sequence includes folding the rotors, opening the mothership's rear port, precisely adjusting the final traction drive for the physical connection, and then actuating the locking pins.
And it has to verify the connection.
Critical verification happens here. The HCU monitors the locking torque applied to the pins to ensure a physically reliable, secure connection that won't decouple during ground movement.
And finally, confirming the power supply is secure, circuit establishment, and system self-verification.
Once locked, the high-voltage plug-in occurs. But before any 800V current flows, the HCU manages sophisticated safety checks. Insulation resistance checks for shorts or ground faults, contact resistance checks for connection quality. Only once that power link is confirmed safe does the VCU-FCC execute a complete rapid network self-check within 30 seconds, confirming all sensors, controllers, and communication paths are online and ready.
The precision, the speed, the cross-checking in this docking sequence. It really embodies the entire safety philosophy of the P-13.
It really does.
We've now established the what and the how. Let's move to the most difficult part of this specification, the safety guarantees. This is where the Automotive, ASIL-D in aerospace, DALA, worlds collide in 4.1, the DLA, and ASIL-D dual mandate.
This is the core tension. The VCU-FCC, specifically the flight control path, must satisfy both standards. It means achieving the highest level of functional safety in both domains. ASIL-D means preventing failures whose risk is considered intolerable.
Like uncommanded acceleration causing a crash.
Right. And DALA, Design Assurance Level A, is the absolute highest level, reserved for functions whose failure would be catastrophic to the aircraft. It mandates a failure probability of less than 10 to the minus 9 per flight hour.
The numbers are stark, but what about the cultural clash? Automotive development prioritizes iteration, cost efficiency, speed. Aerospace prioritizes frozen requirements, proven often older technology, and just incredible documentation rigor. How does the P-13 engineering team reconcile those vastly different philosophies?
It forces a fundamentally rigorous process on the automotive side that is highly unusual. For the VCU-FCC, you have to adopt the aerospace mindset of formal methods, meaning you spend far more time and money upfront proving mathematically that the design cannot fail, rather than trying to patch it later. But the architectural solution to enforce that safety separation is mandated. The ARIN 653 Partitioned Operating System.
ARIN C653 is an aerospace standard for resource management. How does it isolate the automotive faults?
It creates strict enforced boundaries in time and space for software processes. Imagine the VCU-FCC processor running dozens of software applications. ARIN C653 guarantees that the flight-critical partition, the DLA attitude control, is given a fixed time slice and a strictly protected memory space.
So if another part of the system goes haywire,
if the groundside partition, which might manage infotainment data logging, and is only certified to ASIL A, B, or C, has a memory leak or runaway process, the ARIN C653 kernel will isolate it. It prevents the fault from propagating and corrupting the execution of the flight-critical code. This is the only way to achieve certified freedom from interference in a multifunction controller.
that brings us to the physical foundation of trust. 4.2 hardware hardening. DO 254 compliance. This is where we ensure the silicon is as reliable as the software.
For processor selection, traditional chips are just inadequate. The specification demands multi-core lockstep architectures like the NXP S32G3 or the Infineon AURIX TC4X. The principle is simple. Two identical cores run the exact same binary code simultaneously, cycle by cycle. Their outputs are compared by hardware logic in real time.
So if one core miscalculates a floating point operation due to a transient event, it's instantly caught.
Precisely. If the results mismatch, the system immediately flags a computational error, a failure that is often undetectable by software alone. This is often preferred over software diversity because it catches those transient hardware faults instantly, and it saves on size, weight, and power for the eVTOL.
And the memory integrity has to match the processor integrity.
Absolutely. Memory integrity requires error correction code, or ECC functionality, on all RAM and cache. While ECC is standard in servers, it's mandatory here for protection against single-event upsets, or SEs.
From cosmic rays at high altitude.
Exactly. At 10,000 feet, we have increased exposure to high-energy neutrons and cosmic rays. If a single particle hits a memory cell, it can flip a bit, turning a 1 to a 0. ECC detects and corrects these errors before they corrupt a calculation or a critical control law variable. Without ECC, DAL, a certification at high altitude, is practically impossible.
And what happens if the main power source fails suddenly?
The system requires robust power redundancy, specifically demanding a hold-up time of at least 200 milliseconds. Internal capacitors have to maintain sufficient voltage during that power loss event.
Why 200 milliseconds?
That's the time needed for the VCU-FCC to gracefully execute its emergency shutdown procedure, writing the crucial fault logs to non-volatile memory, and, critically, commanding all actuators like motor controllers and clutches into a guaranteed safe, deterministic state before the lights go out entirely. It guarantees the system doesn't shut down mid-command.
Now we move to the specific failure responses dictated by the Preliminary Functional Hazard Assessment, or FHA, in 4.3 Functional Hazard Mitigation. These are preemptive safety laws baked right into the design.
The FHA identifies three absolutely critical hazards. First, FSO1, uncommanded reverse thrust. If the propellers suddenly reverse pitch while airborne, you lose lift and the aircraft falls. It's catastrophic.
So the mitigation logic has to be absolute.
It has to be. The software must strictly prohibit propeller pitch reversal when the airspeed sensors or the flight attitude sensors indicate flight. That reversal function is only unlocked when two independent systems, airspeed sensors and weight-on-wheels switches, both confirm, without ambiguity, that the aircraft is safely on the ground.
That dual cross-checked confirmation prevents a single sensor failure from causing a catastrophe.
Yes. The second hazard is the architect's ultimate nightmare. FSO2, total loss of thrust control.
And this is why we have the limp home mode.
Exactly. The VCU FCC is incredibly complex, running millions of lines of sophisticated code. If that entire system fails, say a corruption of the OS kernel or an unhandled hardware exception, we need a guaranteed backup. Limp home mode requires an entirely separate, simple logic circuit, often an FPGA or a CPLD. This circuit is deliberately simple, non-programmable once deployed, and certified to a lower but proven integrity level.
So it bypasses all the complexity. What does it do?
It cuts through the main VCU operating system and directly reads the pilot's analog throttle or collective stick signal. It then provides basic, open-loop thrust commands to the electric motors. It's not efficient, it doesn't damp vibrations, and it doesn't calculate optimal trajectories.
But it works.
It guarantees the pilot retains basic, critical authority up or down for an emergency landing. Survival in this scenario absolutely trumps optimization.
And the final failsafe requires sub-microsecond reaction time, FSO3, high voltage interlock loop, or HVIL.
The HVIL is the physical safety chain that runs through all high voltage connectors and enclosures on the 800-volt bus. If that loop is broken, meaning a connector is disconnected or a major fault is detected, it indicates a critical hazard, like potential high voltage exposure or irking. The VCU has to trigger a hardware shutdown of the PWM signals to all inverters within less than 10 microseconds.
10 microseconds. That's instantaneous by human standards.
Mm.
Is that a hardware constraint or a software constraint?
It's purely a hardware constraint, and that's the point. No software stack, no matter how fast the RTOS, can guarantee that speed. The HVIL signal has to directly feed into hardware logic that physically kills the PWM signals, bypassing the main processor entirely. Achieving that speed requires careful physical design. It's safety enforced by the laws of physics, not software code.
Beyond computational integrity, the VCU FCC has to survive the environment. This is covered by 4.4 environmental hardening, DO-160G compliance.
And the environmental requirements are brutal. The VCU FCC must operate in temperatures ranging from a deep cold of -55 °C up to +85 °C in the cabin, and potentially up to 105 °C if it's located near the ICE or in the rotor nacelles.
Which presents a serious thermal management challenge.
It does. The sources prioritize passive cooling solutions, conduction cooling, to avoid the reliability risk of fans and pumps. But if active cooling is needed,
And then what?
if the heat density is too high, the cold plate has to be integrated with the low-temperature battery cooling loop. This keeps the thermal architecture streamlined. You don't want a dedicated VCU chiller. You integrate it into the existing safety-certified battery thermal loop.
But the most exotic physical requirement, one that reminds us we are dealing with high-altitude aerospace, is high-altitude electrical safety.
This takes us back to fundamental atmospheric physics. It's governed by Paschen's law. As the aircraft climbs, the air pressure drops, meaning the air becomes a less effective electrical insulator.
Which increases the risk of arcing.
Drastically. It increases the risk of corona discharge, where high-voltage traces on a PCB start to arc to adjacent low-voltage circuits or even to the chassis. This is particularly dangerous for the 800V sampling circuits.
So how does the VCU FCC physically fight Paschen's law?
By enforcing physical barriers, the VCU designers must use strict physical spacing corrections, increasing the creepage, which is distance along the surface of the PCB, and clearance, the distance through the air between high-voltage traces. Or, if space is critical, the entire high-voltage section has to be protected using potting encapsulating the circuit board in a non-conductive solid compound, or applying specialized conformal coating to prevent electrical breakdown at altitudes up to 30,000 feet.
It's an example where the electrical engineering design has to directly account for reduced atmospheric density. Just Incredible.
Hmm.
Designing the VCU FCC to meet this dual mandate is monumental, but proving it works is equally rigorous, especially when seeking DALA certification. The entire development process follows the highly disciplined 5.1 Prior, the V-model integrated verification process, moving from simulation to physical reality.
The V model is a structured approach that de-risks the design progressively. We start with the software layer at the very top of the day.
Stage 1, processor in the loop, PIL. We're testing the code here, aren't we?
We are testing the compiled code. Since the P13 uses model-based design from Simulink and Stateflow, the critical control software is auto-generated. PIL verifies the numerical integrity of that auto-generated code when it runs on the actual target lockstep processor.
So you're checking to see if the compiler introduced errors.
Exactly. We check the efficiency. Does it meet the sub-1 timing requirement and the numerical fidelity? Does the floating point math result in the exact same output as the high-fidelity model running on the development PC? It's the gate check.
Once the code is proven on the processor, we integrate the entire simulated world around it in Stage 2, hardware in the loop, HIL.
HIL is the virtual aircraft simulator. We take the actual VCU FCC hardware and plug it into high-fidelity real-time simulators like DSpace or NIPXI systems, which simulate all the physics. The dynamics of the 8 rotors, the K0 clutch, the battery SOC, the wind gusts, all 200-plus I/O signals.
This is where you run the extensive fault injection testing.
Right. The source has specified over 200 fault injection scenarios.
What are the engineers trying to break here?
They are trying to verify the fault tolerance and the failover logic, that entire 10 to the -9 safety promise. They simulate loss of power to one core, short circuits on sensors, data corruption on the slum bus, and, most importantly, they verify that the automatic failover to the backup VCU happens in under 20 meters, and that the limp home mode activates correctly when the main processor is deliberately frozen.
So HIL is designed to catch flaws in the logic before real hardware is ever put at risk.
Exactly.
Before the final assembly, there's a crucial electromagnetic test stage, Stage 3, Copperbird, EMC-EMI testing.
The Copperbird is specialized for testing electromagnetic compatibility and interference. This test focuses exclusively on the noise profile. The VCU FCC is powered up under real 800-volt high-current switching conditions, the exact environment it will face in the aircraft nacelle.
And you need to be sure that the noise isn't corrupting the control signals.
We need absolute assurance that the incredibly strong electromagnetic fields generated by the high-frequency suit inverter switching do not induce noise or crosstalk onto the sensitive, low-voltage control signals, especially corrupting the integrity of that dual-redundant CAN-FD network. If the EMI corrupts the timing or the data, the entire system is non-deterministic.
And the final hurdle, the ultimate physical proof that the regulators will demand. Stage 4, Ironbird integration test.
The Ironbird is the physical twin of the propulsion system, using 1.1 scale, real hardware. It includes the actual VCU FCC, the batteries, the inverters, the full ICE and P1-P3 motor stack, and the K0 clutch, all connected to physical load stands that simulate the drag of the rotors.
So HIL proves the logic works. The Ironbird proves the hardware works.
The hardware works in concert with the real physics of high-power components.
Yeah, and the specific test required here.
To achieve durability and certification, the system has to execute 10,000 continuous mode switching cycles pure electric to parallel hybrid and back again. HIL can simulate this logic, but only the Ironbird can verify stability against real physical shocks, heat cycles, component wear, and timing delays inherent in mechanical systems. This test catches latent failure modes that only manifest after thousands of cycles.
All this effort is quantified against measurable metrics. 5.2 Final Acceptance Criteria, KPIs.
Starting with the core performance, ACER1 real-time performance. The control loop time has to be stable under 1 millisecond. T-Addernet jitter less than 50 microseconds. This confirms the deterministic architecture is actually functioning as designed under load. If you fail this, the system is not getting certified.
Next, operational readiness, ACO2 system availability.
Cold start to ready for thrust status must be less than 5 seconds. Passengers expect instantaneous readiness like a modern car. A 30-second boot sequence is just unacceptable for high-utilization UAM operations.
And the test of the redundancy, ACO3 fault recovery.
This verifies the dual duplex architecture of the VCU. The time required for the backup VCU to seize control after the main unit fails must be less than 20 milliseconds. But the crucial follow-up metric is the result. Total thrust fluctuation during that failover must be minimal, less than 2%.
Any higher fluctuation risks the FCC losing attitude stabilization momentarily.
Correct.
And finally, the certification standard for the code quality itself, AC04 software integrity.
For DLA software, we are mandated to achieve 100% modified condition decision coverage, or MCDC. This is the highest rigor standard for code verification. It ensures that every condition within every decision statement in the critical flight code has been tested independently, guaranteeing that no hidden logic paths, no matter how complex, remain untested.
This requirement is why DLA software development often takes 3 to 4 times longer than standard industrial software.
Oh, at least.
The mode switch reliability metric reinforces the Ironbird testing. 1,000 continuous switch cycles with 0 mechanical shocks or logical deadlocks. This is the synthesis of everything we've discussed.
Perfect software orchestration leading to physical, real-world smoothness and reliability.
That is a phenomenal deep dive into what must be one of the most complex control systems currently being engineered. The VCU FCC isn't just a component. It's the entire engineering philosophy of the P-13 long-range capability powered by hybrid systems, wrapped in layers of aerospace-grade safety.
Indeed. It is the embodiment of determinism, integrity, and redundancy. It's what grants the P-13 the long-range advantage of hybrid power while achieving safety levels equivalent to commercial airliners, that 10 to the -9 probability of catastrophic failure per flight hour. The successful development and certification of this digital brain is, without question, the single most critical dependency for P-13 achieving its operational mandate.
And as our sources stress, the next phase of development has to focus on immediate deployment of advanced model predictive control, or MPC-based energy management strategies, to squeeze every drop of efficiency out of that hybrid powertrain. But ultimately, the real barrier isn't the code. It's into the construction of the full-scale Ironbird platform, which is the only physical integrated evidence that the ESA and FAA will accept to grant final type certification.
And this brings us to a final provocative thought for you to chew on. We've established that the VCU FCC has to handle a catastrophic failure by immediately switching from its advanced, optimized control algorithms, which utilize model predictive control to forecast optimal energy use 10 minutes or 600 seconds into the future, to a simple, guaranteed safe, limp home mode run on basic FPGA logic.
So that switch happens, all the foresight is lost.
It's gone. The system reverts to basic present moment inputs. In that moment of highest danger, when the system jettisons all optimization for basic survival, does maximizing immediate flight control and integrity relying only on present inputs, ultimately compromise the pilot's tactical ability to successfully execute the emergency landing, having lost that 10 minutes of advanced energy foresight.
And how does the pilot manage the tactical and psychological shock of that instantaneous loss of automation?
That shift is something every engineer designing these systems must grapple with.